function of the Biot number, the characteristic length, to determine that can be calculated using the length divided by the surface area. And remember, this approach is just valid for lump systems. You're going to see as we start to go through the material now that you cannot do that in general. Right, so Paragon is continuing. System approach, all those temperatures, the temperatures as function of time, temperature as function of time, all those points 1, 2, 3
the same solution. So it would not say that this temperature is 100 and that one is 90 and that is 80. It would be 100 everywhere. With the approach that we're going to follow now, temperature as a function of time, here we're going to have different time temperature variations, something like that, and that is what we are interested in this paragraph, and that is what we are not going to solve in this paragraph. Okay. So from chapter 2, now we're going to look at the mathematics a little bit. From chapter 2, you have already derived a heat conduction equation in 3 dimensions, and it looks like this. There's partial d2t dz squared plus Egen divided by k is equal to 1 divided by alpha dt dt. The one t, capital T, is for temperature, and the other t is for time. And this alpha is the thermal diffusivity. If you can't remember, it's the thermal diffusivity. It is equal to K divided by rho Cp. So that is the general equation in 3 dimensions. If we look at these types of problems, which are the simplest types available, then we will see that the heat transfer rate is in 1 dimension only. As we said, there are no temperatures or heat transfer coming from here, from the top and the bottom. Everything is in 1 dimension only. It would therefore mean that if you've got the temperature, remember this is very long, if you've got the temperature at the center at this point, then it would also be the temperature at the center there, and it would also be the temperature there. This temperature would be the same as there, and there, and there, and the same there. So therefore the heat transfer rate is in 1 dimension only. So for that reason, we are not going to consider those 2 terms, and that is then the general heat conduction equation, which is now valid for this problem. So the differential equation, the first one there on the slide, there it is. You've got it there. And let's just look at typically the boundary conditions. Let's suppose that is the temperature, Ti, through the plane wall or the cylinder. And then suddenly the temperature is increased to T infinite on the outside. Let's suppose this temperature is 0 and that temperature is 100. What would we expect with the temperatures? What will happen at the temperatures? Well, firstly, we can expect that the temperatures on the side is going to increase, isn't it? Because they are the closest. So we're going to have a temperature distribution typically like that. And because of symmetry, if it's 100 degrees on this side and 100 degrees on this side, then that temperature and that temperature is going to be the same. Okay. So my curve is not that good, but it should be symmetrical, and that gradient there should be equal to 0. And then a few seconds later, it will do something like that. Okay, do you agree? And then later on, this temperature in the center is going to start decreasing. You're going to start getting something like that. Until a very, very long time, then the temperature right to the body would be T infinite, that of the outside temperature. The important thing here is the boundary condition that we have here. And the boundary boundary condition says that this gradient is equal to 0. That's the first boundary condition that we need to solve this problem. Then the second boundary condition is to say that the conduction heat transfer into the body is equal to the convection heat transfer into the body. Now that boundary condition says minus K multiplied by the area partial dt dx is equal to the heat transfer coefficient multiplied by the area multiplied by the temperature minus T infinite. Okay, the areas of course would cancel out. And then we've got an initial condition. Any partial differential equation needs an initial condition to start with, and that initial condition is very easy, and that is that when T is equal to 0, then the temperature throughout the body is equal to Ti. Now to solve this partial differential equation, what has been done is to write it in a non-dimensionalized format. So we've got capital X, which is equal to small x divided by L. What is small x? Small x is just this distance. Okay. So there, capital X would be equal to 0, and there it would be equal to 1. Okay, because x is equal to L. So it means that the distance is always non-dimensionalized. It will always be between 0 and 1. Then we also non-dimensionalize the temperature, which is equal to the temperature, which is a function of x of t minus t infinite divided by Ti minus T infinite. Non-dimensionalized temperature. It would therefore means that if we write it, if this is, okay, here on the outside, we should actually put T infinite there and T infinite there, I forgot. The heat transfer coefficient H, and it's the same with all the other bodies. And initially, the temperature is equal to Ti. T is equal to Ti, and T is equal to Ti. Okay. So that non-dimensionalized temperature tells us that if that temperature is suddenly 100 and that was equal to 0, okay, and you go and calculate it, then you will always see that depending on if the temperature is originally at Ti or later at equal to T infinite, the non-dimensionalized temperature will always be between 0 and 1. The Biot number we've done with the previous lecture is equal to the heat transfer coefficient multiplied by L divided by the thermal conductivity K. It's the Biot number. And the Biot number is the dimensionless heat transfer coefficient. HTC is heat transfer coefficient. I'm going to use it a lot in this module because it's a very important thing that we're going to use a lot. The dimensionless heat transfer coefficient, the Biot number. Then, what is also defined is tau, which is alpha T divided by L squared, is equal to the Fourier number, and that is the dimensionless time. And again, this time will then always varies between 0 and 1. No, sorry, it wouldn't vary between 0 and 1. So, why are we doing all this stuff? Where are we going to? Well, what was done by non-dimensionalizing all these numbers, the Biot number, the Fourier number, etc., is that Of this body at different positions inside it and maybe even on the surface. If we have steady state heat transfer, steady state, and we would look at all the temperatures, then the temperature as a function of time, and that is the very important thing here, then the temperature at point 1 will stay constant as a function of time, as well as the temperature at point 2, temperature at point 3, and maybe there's the temperature at point 4. So there are no changes as a function of time. However, if it is transient, then the temperatures as a function of time would change. So that might be the temperature at point 1, that might be the temperature at point 2, the temperature at point 3, etc. So transient means it is dependent on time. And therefore we would like to get the temperatures as a function of time. The first paragraph is called lumped system analysis. Lumped system analysis. What does lump mean? It means it behaves the same, and it would mean that if we look at different bodies,
don't know.